afternoon. What I'd like to do today will be to discuss some of the issues relating to the remediation of chromite ore processing residue, or copra, in the Glasgow area. What I'd like to do first of all is to tell you a little bit about the historical issues relating to the development of a treatment for copper, particularly hexavalent chromium, to focus on some of the particular problems with treatment in this particular matrix, and look at some of the potential for using chemical reduction on copper and how this fits into the remedial strategy. The site we're focusing on is Shorefield, which is to the southeast of Glasgow city centre, which is a key part of the Clyde Gateway Regeneration Initiative. This is a 25-year programme involving something like £1.6 billion in private investment. As it happens, however, the city of Glasgow was host to what was the largest producer of chromium in the world, in operation from about the mid-19th century to closing in the late 1960s. During this time, something like 1 million tonnes has been estimated of chromite ore processing residue, elevated hexavalent chromium, has been used as landfill material in and across southeast Glasgow, particularly for areas where there was clay mining for local brickworks. This has resulted in significant environmental liabilities, particularly resulting from hexavalent chromium, which you can see here is typified with these yellow nodules in this trout being excavated through a contaminated zone. This gives you a very simplified conceptual site model. I think the key thing to point out here is the nature of some of the hotspots of chromite ore processing residue, and the fact that this has been deposited below the water table, so that you have an ongoing source of hexavalent chromium impacting some of the local streams, the Almaty Burn particularly, ultimately providing the base flow to the River Clyde. The actual risks to human health can be engineered fairly easily using conventional capping containing seeds. It's the controlled waters receptors where the key liabilities are posed. This just shows the site again by the River Clyde and some of the previously identified chromium contaminated sites in Glasgow. A few of these have already been capped in Campus Lane, Myrtle Park, a residential area, but most of them clustered around the Shorefield area. That's the former chemical works located adjacent to it. This shows you some of the depths to which the copper is deposited. The deepest areas go down to about 12 metres, again typified by these pits that have been dug for clay mining, which have been infilled with copper. Concentrations of chromium are typically above 2,000 milligrams per kilogram. These are the deepest red blobs in the affected areas. Hexavalent chromium, variable, but can be anything up to thousands of milligrams per kilogram too in the soil. In the groundwater, so you can't read that very well, but these blobs are over 100 milligrams per litre, the deep red blobs. So you can see getting into quite high concentration, at least in the tens, and typically in the worst areas up to hundreds of milligrams per litre. That shows you a lump of chromite ore processing residue. So what are we actually trying to do here? We're trying to convert the hexavalent chromium, which is known to have high toxicity, which is a known carcinogen, to chromium-3. Essentially this, which you can actually buy as a dietary supplement, a relatively benign sort of compound. We're also looking to reduce the mobility of chromium because the chromium-3 is actually relatively immobile when it's in a neutral to slightly alkaline environment. If you increase the alkalinity to a very high pH, it does remobilize, but I'll come to that later. We conducted a detailed quantitative risk assessment for the Shorefield site using a mass balance approach, defining catchments based on the drainage pathways carved out by some of these surface water conferences. And as part of this, there's a requirement that we've identified to actually culvert some of these to improve the culverting that exists already with these localized burns through a conventional engineering approach to stop short circuiting. Taking that approach, but taking a mass balance through the base flow from the groundwater, we've come up with provisional remedial criteria for the groundwater of something like 200 micrograms per litre of total chromium. That's based on achieving the PNET water quality standards, which are around 30 micrograms per litre within the river. These criteria, however, are provisional and yet to be fully negotiated. So copper itself does provide a key challenge, and some of the early work that we did about 15 years ago, which was financed by Syria as well as Glasgow City Council, highlighted some of the problems and limitations of conventional treatments for chromium-6 when in this type of residue. A large-scale research program was undertaken by the University of Edinburgh and the Macaulay Institute, which we were involved in as an end user, to look at some of the geochemical issues relating to the distribution of chromium within chromite ore processing residue, defining the particular mineralogical phases. And this highlighted some of the issues that demonstrated why some of these techniques were not as appropriate as they would be in an ordinary soil matrix. Around the same time, some of our colleagues in the US, together with other consultants, were having some good success with another reductant called calcium polysulfide, or as it's more commonly known, lime sulfur. We've successfully applied this, as I say with other people, to reduce chromium plumes, particularly plating works, but not at that time in copper. We therefore did some more collaborative work sponsored by Eden, one of the Entrust companies, and on the basis of successful reduction at laboratory scale, we moved on to do an ex situ field trial, set up in various skips of material contaminated with hexavalent, with copper contamination, which demonstrated good reductions through the use of calcium polysulfide. This shows some of the effects of the trials. When we looked at this concentration was what had been successful at lab and the bench scale. These were the concentrations apportioned according to that, and we were getting down to concentrations in the order of 1 or 2 milligrams per kilogram just after a day, coming down a little bit further after 13 days, starting concentrations in the 700 to 800 milligram per kilogram range against the control. Particularly important in terms of groundwater, obviously, is the leachable aspect of this. So we looked at leachable total chromium, and you can see again good reductions by these treatments, getting down to 2, 3, or even less than detection limits for total chromium after a day using basically that was just using a simple NRA leach test, and similar results using the analysis for hexavalent chromium, colorimetric method. Some discrepancy between the two methods, nothing really significant just because of the higher reporting limit for the hexavalent chromium method, but essentially showing pretty good reduction in the concentrations. We then moved on to do a field trial, a very simple in situ field trial, which simply involved pouring down a diluted concentration of the stock solution to a single well and monitoring the groundwater concentrations. There were some changes in chromium-6, only in the immediate vicinity, and one of the key problems was the reactivity of the calcium polysulfide was resulting in the blockage of the formation by the reaction products calcium sulfur and probably chromium hydroxide itself. So the basic conclusions that we ended up with from these initial studies was that yes, the copper was indeed treatable by calcium polysulfide, but the key thing was to ensure appropriate distribution through the matrix. First of all, to establish contact, which Jeremy is often mentioning in relation to the oxidation products from jumps. Exactly the same thing when you're looking at reduction. You've got to establish contact with the material, and also to prevent these reaction products from forming and creating a impediment for further import into the saturated zone. So deliverability was the key issue in the trials, in the development of treatment. So we then looked at last year a deliverability trial to examine 3 ways of getting calcium polysulfide into the subsurface. We looked at the groundwater circulation trial, a direct injection trial, and deep soil mixing. The trials were all carried out on this site. We had good spacing between them. For the groundwater recirculation trial, we were looking at a 5 by 5 metre plot. Abstraction was taken from a central well, and the groundwater was then re-injected following treatment with amendment with calcium polysulfide via these 4 injection wells. And we had a network of monitoring wells set up to look at the changes in the geochemistry. That shows the setup we had. So we had an abstraction well, mixing tank. What we were doing here was simply to add sufficient calcium polysulfide to take out the chromium-6 within the stream, so that we would avoid having the problems of impediment when we were leading groundwater flow through blockage of fines of particulates and everything else. So we had a polishing filter, and then most of the calcium polysulfide was then dosed after this, using the groundwater essentially as a means of conveying this to the subsurface to actually achieve in situ chemical reduction. That just shows the setup, and the 5 by 5 metre plot works for here were done by GRS. And this shows the results. Note, first of all, I've plotted this on a logarithmic scale, so we're going from 1,000 milligrams per kilogram, a little bit less than what we would originally looked at treating, 100, 110 and 1. This shows the total chromium. Note that there was actually a slight reduction there, possibly some loss through mobilization of total chromium, which I'll come back to in a minute. The hexavalent chromium falling from just in the hundreds of milligrams per kilogram to just in the tens of milligrams per kilogram over the 2-week or so treatment period. We looked at the soil leachate. Again, here we actually have a bit of an increase afterwards. What I would point out here, however, is this is not on a log scale, this is an ordinary scale. First of all, there's quite a lot of noise on this. I haven't plotted out the standard errors on this because it's not actually normally distributed. But the thing to note as well is that we took some of these samples from the unsaturated zone as well as the saturated one. So what you're seeing, obviously, with the groundwater circulation is having less of an effect there. If we move on to the actual groundwater concentrations, and again, note this is plotted on the logarithmic scale, so back to log scale. First of all, looking at the first 3, times 0, T2 and T3, concentrations of total chromium in the groundwater largely present as chromium-6, falling out quite nicely by 2 orders of magnitude. Hexavalent chromium also coming down. The difference here is because of the raised reporting limit. There were a number of interferences with the hexavalent method which raised the reporting limit. That's why we see it slightly higher there. These are inclusive of all the monitoring wells. This shows the same thing, T0 and T7, but this shows all the wells, including the injection wells as well as the monitoring wells. So essentially, again, you're seeing reductions in the total chromium in groundwater and reductions in the hexavalent. That's how it will be seen on a full-scale conceptual design, essentially creating a in-situ reactive zone through this recirculatory mechanism to effect in-situ reduction. Moving on then to direct injection. Here we have something like 12 injection points over a 6 by 8 metre plot. This trial was actually performed by ERS. We had 50 millimetre monitoring wells set in similar numbers previously within the actual plot, 6 by 8 metres. And we carried out, ERS carried out the direct injection using bag wells injecting from the base upwards at 200 millimetre intervals. Direct injection technique, achieving fairly closely spaced intervals, 2 metres or so, going up towards ground level. That just shows the rig direct injection trial. So you have to drill through the path standing there. And this is the results of the soil. Again, notice a slight reduction in the total chromium. This is a log scale, not very much, probably not significant. You can see quite a good fall off there in the chromium, hexavalent chromium contamination between previous and following direct injection. Leachability, actually dealing with the hexavalent chromium first, getting some reduction there, rather raised reporting limits, so this may have come down quite a bit more. We're actually seeing an increase in the total chromium, so that difference is actually the chromium 3. Interestingly, that's coming through because you're getting a remobilization of the chromium 3 at these very high pHs. That's probably the reason. It's already quite high in pH, about 12 or 13. You're probably getting a little bit more there through the treatment. In the direct injection, again getting good reduction in the chromium 6, though there were some interference effects there, hence there was a bit of a discrepancy with the total chromium results. Moving on to the soil mixing trial, we've got here again a 5 by 5 metre plot. On this occasion, because of the nature of the soil mixing, we only had one post-application borehole drilled in the sand. We had soil sampling boreholes, but the one we installed the well afterwards, but we have monitoring wells out with the plot. So just know you're not quite comparing light with light in terms of the actual groundwater concentrations on a trial-to-trial basis. That's essentially the basis of the soil mixing trial. You have these continuous flight augers creating a series of vertical soil columns, overlapping soil columns. So you've got injection phase, breaking down the soil, adding the calcium polysulfide, then removing. That shows the continuous flight auger is going down. You can break out this area, of course, just a 5 by 5 metre plot. This shows the results. Note again, slight decrease in the total, but quite a significant reduction there from the hundreds of milligrams per kilogram in the hexavalent to between less than 1 milligram per kilogram post-treatment. Soil leachate 2 coming down from 100 milligrams per kilogram, this is using the new tests, to less than 0.1, and similarly with the hexavalent. Here we're getting to the reporting limit, so that's actually just at the reporting limit, which was actually raised from the detection limit, again because you do get a number of interferences, meaning you have to actually dilute the sample into that. As I mentioned, the groundwater was actually taken outside the plot, so we don't actually see quite as dramatic a, quite not a huge effect, but we are quite close to the detection limit to start with. The groundwater concentrations of hexavalent chromium were not that high in this particular part of the trial site. Just one of the things you have to live with, I'm afraid, with these trials is the heterogeneity of the ground conditions. Note again, a bit of an increase here in the total coming through, possibly a remobilisation of the chromium 3, but this too dropping after time. So it does seem to be relatively transient, where we do have the remobilisation. That just shows how it will be scaled up. You can extend this below the saturated zone. That trial was done through the entire thickness up to 10 metres depth, so you can actually extend that through there for the full-scale treatment. This just summarises the soil concentrations. I've done it as maximum and mean. As I mentioned, they weren't normally distributed. We've actually done some quite detailed non-parametric statistics on this, which we're going to hopefully publish in a Claire publication. So recirculatory trial, mean coming down quite well on some of these treatments. One thing I will point out though, on all of these, you could still see some unreacted chromium 6 within the treated soil, even on the soil mixer. So, we shouldn't run away with these figures tell us everything about it. Soil, going on to groundwater concentrations, 300 is the reporting limit. Say it's raised, it's normally about 10 or 30, but it is raised reporting limit because of a number of interference effects, but again, getting down essentially the same sort of order of concentration following treatment. So all the treatments achieved good reductions in soil concentrations. There was some visual evidence, and even with the soil mixing trial, there was still some presence of yellow nodules. No treatment is going to work 100% on this. It's clear to do that even after post-treatment. groundwater concentrations coming down typically to below the reporting limit. But having said that, there is still this issue of total chromium. Despite the fact you can actually buy this, and eat it with total chromium, this is still, a treatment objective to actually get the concentrations of total chromium down at the receptor. Now, because it's mobilised at the very high pHs, and the pH does drop quite significantly outside these areas, along the flow path to the river, then it's quite likely, very likely, that you will get natural attenuation taking place, so the chromium hydroxide will then precipitate out to the chromium-3 before it reaches the river. The chromium-6 itself also does seem to be showing a strong natural attenuation outside the particular areas that we're treating, because it's been there for over 100 years. There's quite a high organic matter content in particularly the alluvium below the pits, and that does seem to have had some effect in causing a natural reduction. So just to essentially sum up, see the time's coming up now. What we've done over here, I think we've got a pragmatic remediation criteria. We've still got to complete the negotiation of this secret here, but the mass balance model certainly seems to be appropriate here for factoring in the dilution, coming up with a defensible, pragmatic strategy for the areas actually requiring remediation. Because clearly this is expensive material, we don't want to be having to treat more than we require. Obviously from a sustainability point of view as well. We invested a lot of time over the years, or the client has particularly, in looking at why conventional chromium-6 treatments don't work with this sort of material. John Farmer's group in the University of Edinburgh have published quite a lot on this, and is interested. Essentially, for us to spend quite a bit of time looking at deliverability issues and avoiding loss of permeability. And one thing I did touch on, but hopefully we've got time to go into it in detail here. Again, hopefully this is something we can refer to in the Clare publication, looking at the various methodologies quite critically, and overcoming some of these interference effects, which are quite significant, particularly the actual addition of calcium polysulfide itself. Verification being a lie to that, and going back to the combination of techniques, we're not saying that any one of these three particular techniques such as trial is better than the others. They've all got a role to play in different environments. Some are going to perform better than others, some are just not going to be practicable to implement, and some are obviously going to be limited in terms of the final concentration achievable. So that brings us on to the final point. Natural attenuation will clearly have to play an important role. So thanks so much for that. I think I've acknowledged everybody. I did actually include the acknowledgement slide that's on there. Various parties involved in the work. Particular thanks to Clyde Gateway, Glasgow City Council for allowing us to present this presentation. Thanks so much.